Okay, dear students, now we will move to the principle of EPR spectroscopy principle. That means how it actually works. We know that as we already studied that the electron can have two type of spins. That means it can have a clockwise spin like this, or it can have a anti-clockwise spin like this. And I also told you that the two type of spins will have magnetic moment which are anti-parallel. As I told you that in case of the clockwise, the magnetic moment is in the downward direction, while in case of the clockwise spinning motion, the magnetic moment, spin magnetic moment of it will be upward. So when there is no magnetic field, when there is no external magnetic field, at that very time what will happen, the electron, the unpaired electron, can have any one of the two spinning motions. So it can actually spin in the clockwise direction, ms is equal to plus 1 by 2, or it can spin in the anti-clockwise, that means it is spin angular momentum quantum number is minus 1 by 2. So the two orientations are equally probable in absence of the external magnetic field. At that very time, we can say the two spinning orientations are degenerate. That means they are of equal energy. However, when we apply the external magnetic field, for example, we apply the external magnetic field B naught in this direction, what will happen? This spinning motion, which clockwise spinning motion, what will happen in this case? What will happen? The magnetic, it is spin magnetic moment, it will oppose the external magnetic field. It will oppose the external magnetic field. While in case of this anti-clockwise spinning motion, it is reinforcing the external magnetic field. It is very much analogous to the NMR spectroscopy, which you might have already read. So what will happen? The spinning orientation, which actually opposes the external magnetic field, it is magnetic moment when opposes the external magnetic field, it will rise in energy. Similarly, when a spinning orientation where it is spin magnetic moment actually reinforcing the external magnetic field, it will decrease in energy. So what will happen? Firstly, when there was no magnetic field, the two orientations were degenerate. That means ms is equal to plus 1 by 2 and ms is equal to minus 1 by 2. They were degenerate. But once the field was applied, what will happen? There will be splitting of the energy levels. The one which opposes the external magnetic field will rise in energy, and the one which actually reinforces the external magnetic field will decrease in energy. So this will correspond to ms is equal to minus 1 by 2, and this will correspond to ms is equal to plus 1 by 2. It is called alpha state, this is called beta state. And the energy difference between the two, this energy difference between the two, it is delta E. It will be given by h nu. So when the external magnetic field is applied, there is no degeneracy now, and the two spinning orientations will behave differently, and there will be splitting in the energy levels. And here you can say it is no field, because no magnetic field was applied here. Here magnetic field was applied. Okay, so when the two energy levels have splitted now, and there is an energy difference between the two. So now comes the concept of transitions. So now there is probability of the transition from this beta state to the alpha state if it absorbs a particular frequency which is equivalent to the energy difference between these two energy levels. So if you increase the magnetic field, if we increase the strength of the external magnetic field, this energy gap will increase. As a result, we need much higher frequency to actually undergo this transition. So similarly, we can understand it through some another way. That is, for example, this is the external magnetic field B naught, and this is the spinning electron, and this spinning electron is, for example, it is in anti-clockwise or it is in clockwise direction. As we know, it will create its own magnetic moment, and there is one more magnetic moment due to the external magnetic field. The two are not in line, so there is generation of a torque. That what that torque will do, that torque will actually make this electronic the axis of this electron to precess around the axis of the external magnetic field. So it will precess the axis of this spinning electron. It will precess around the axis of the external magnetic field. So there will be some frequency of this precession, and that precession, that frequency is called Lormer precession frequency. Lormer precession frequency. It is a frequency with which it precesses actually around the axis of the external magnetic field. So if we actually want to flip the spin of this electron, how it will happen? When we will put some energy on it, h nu, electromagnetic radiation of some particular frequency, when we put it, it will absorb only when the Lormer precession frequency of the spinning electron is exactly equal to the frequency which we have applied. So when the frequency of the electromagnetic radiation it matches with the Lormer precession frequency of the spinning electron, only then the absorption of this radiation will occur here. So as a result, what will happen? If it was in anti-clockwise direction, it will flip its spin and go into the clockwise direction. That means firstly it was in lower in energy, now it will move to the higher energy state, that is clockwise alpha state, which we can say. And if we increase here also, if we increase the strength of this external magnetic field, it will start precessing around it, the spinning electron will precess around it with a larger frequency. That means as we increase the magnetic field, the precession frequency will be higher. So we need higher frequency actually to undergo the absorption over here. This is actually the phenomenon of resonance. That is why it is called electron paramagnetic resonance spectroscopy. So resonance occurs only when the frequency of this incident electromagnetic radiation exactly matches with the Lormer frequency of the spinning electron in the presence of that external magnetic field. Okay, dear students, now you can you actually understood how the transition can occur in case of this EPR spectroscopy and how they can give a signal. And the signal is actually corresponds to this transition which occurs here. So we now we will move to the another concept, that is how actually we can make the samples in the EPR spectroscopy, the sample. in EPR spectroscopy. Later on we will come to some advanced concepts in this like hyperfine etc. that we will come in the subsequent lectures. First we should know that what kind of samples we can use in case of EPR spectroscopy. One thing is there that we can use samples in solid state, in liquid state, in gaseous state, or in solution phase. Means we can use the samples in EPR spectroscopy in any one of these phases. The another thing is that since this EPR spectroscopy is a very sensitive technique, so we must actually avoid trace impurities. Means if there are some trace impurities of the magnetic electron spin containing magnetic electron spin containing impurities are there in the sample, then it will intervene with our EPR spectrum and will give the misleading result. So we must avoid these trace impurities, and that is why, because of this, actually we use silica based sample tubes, not glass. We use silica based sample. That means we use pure silica based sample tubes and not glass. Why? Because glass may contain some metallic ions like iron 3 positive etc. So they can intervene in the EPR spectrum during the analysis. So we use pure silica based sample tubes. One more thing is there that we should degas the sample. Degassing is important. What does that mean? When we do the experiment in case of a solid sample or a liquid sample, what we should do, we should degas the sample. That means the unwanted gases should be removed from the sample so that they may not intervene with the paramagnetic spectrum of our interest. Like there can be oxygen molecule, atmospheric oxygen that can intervene. So the degassing should be done first while we start an EPR experiment. One more thing is there that sometimes we actually need low temperatures. Sometimes we need low temperatures. That means the sample actually that is not stable at the high temperature. We need to actually do the analysis at the lower temperature. What shall we do at that very time? At that very time, actually we are cooling the atmosphere by liquid nitrogen or liquid helium, but there is some technicality in that. We should not actually lower the temperature gradually. We should actually lower the temperature with abruptly. That because if you will decrease the temperature gradually, there is possibility that there may be some phase transitions in the crystal structure. That means the crystal may change into some another crystalline phase, and that will give misleading results. So the cooling should be very abrupt so that there is no phase separation, and the same phase will be there which we actually want to analyze. So cooling should be abrupt to avoid phase separation. That means crystalline phase separation. There should be no change in phase of the crystalline structure during cooling the sample. So one more thing is there. Water is not considered a good solvent. Water is not considered a good solvent. Why that it is like that? It is because water has high dielectric constant. High dielectric constant. If it has high dielectric constant, it will lead to dielectric losses. Means there can be heat losses. So likewise there can be microwave heating. As you know that microwaves generate heat in water, microwave heating can be there. So generally water is not considered as a good solvent. So in that case we should use that type of solvents which actually have lower dielectric constant and which are easy to handle also. That means they should not be having they should not be that much of, they should not have higher boiling point or that, like or things like that. Similarly, it has been generally observed that free radicals give sharp spectra. The free radicals give sharp spectra. It is because the free radicals generally have the electron in an orbital, which a single electron in an orbital, which is not much influenced by the immediate environment around. So they give sharp signals. But in case of transition metal complexes, they give broad spectrum. Transition metal complexes give broader spectrum. Why they give broad spectrum? That is because there can be spin-spin relaxation effects. For example, we have a spin excited state of a spin that will relax into the ground state spin of the adjacent molecule. So in case of transition metal complexes, so what we generally do to avoid this, we sometimes need to dilute the samples if they are in solution phase, or at that very time what we can do, we can actually dilute the sample. By diluting the sample, what will happen, the molecules will be further from each other and these spin relaxation effects will be mitigated. So in case of solution phase samples, we can easily do the dilution, but in case of the solid samples, it is a bit technical to do the dilution, because it is not like that we will put some powder in our sample and dilute it. It is not like that. We have to dilute the solid sample. Solid sample should be diluted, is to be diluted at the molecular level. Means that the solid sample which we have, that that is to be diluted at the molecular level. What does that mean? That means that, for example, if we will recrystallize the sample, we actually need to recrystallize the sample. While recrystallization, what we will do? The solid, we will first dissolve the solid sample in some solvent, and then we will allow it to recrystallize, so that it will again separate into a crystalline phase. At that very time, we will add some diamagnetic substance. We will add some diamagnetic substance at that very time, which is isomorphous with our sample. What does that mean? That means while recrystallization, we will add some diamagnetic substance in that very solution, which is isomorphous, and first that is diamagnetic. That should be diamagnetic actually, so that that will not interfere with the magnetic properties of our sample of interest. So that should be diamagnetic, and also we should that should be isomorphous. That means that should not have same crystalline structure as that of our sample, so that on recrystallization the both will crystallize together and they will form a single phase, and the molecules of our sample will be further apart from each other. At this in this way, we can actually dilute a solid sample in EPR spectroscopy. So moving forward, now we will see how actually the instrument works. The instrument. As you already read that in case of EPR spectroscopy, we actually depend on two things. One is so as to undergo the resonance, or so as to undergo the transition between the two energy levels. That is external magnetic field. One is external magnetic field. And second is the frequency of electromagnetic radiation. So two things we actually use in this instrument. One is external magnetic field, and another is the frequency of the electromagnetic radiation. But what we do, similar as in case of NMR spectroscopy, what we do, we keep one thing constant and we vary the another thing. We can actually fix the magnetic field and vary the frequency, or we can fix the frequency and vary the external magnetic field. But it is said that it is wise to keep frequency constant and vary the magnetic field. It is wise to keep frequency constant and vary the magnetic field. Why it is so? There are two reasons. One is that we know that in this type of spectroscopy, the frequency actually which is being exploited is microwave. It is microwave, and it has a and frequency is of the order of 3 centimeter in case of 9 gigahertz. 9 gigahertz frequency is actually used in most of the instruments, and it is wavelength lambda, it is of the order of 3 centimeters. So that means the wavelength of the frequency which actually we use in these instruments, it is a bit considerable, you can say. So while using these kind of microwave frequencies, we actually need to tune the sample vessel. Tune the sample vessel according to the frequency used. So we have to tune the sample vessel according to the frequency used. So it is better to keep frequency constant. Why? Because we cannot actually we cannot actually tune the vessel every time with the changing frequencies. So it is better to keep the frequency constant. And another reason is that magnetic field changes with temperature. We know that magnetic field changes with temperature. In case of these experiments, while doing these experiments in the instrument, there can be dissipation of heat, so there will be fluctuations in the temperature. At that very time, what will happen? This magnetic field will show some fluctuations. So if we will keep magnetic field constant, it will be very difficult in those situations when temperature is fluctuating. So it is wise to keep magnetic field varying and keep the frequency constant, because it is easier to keep the frequency constant and to vary magnetic field because of its temperature dependence. Most of the instruments which actually are in the market, they operate at 9 gigahertz. As I said, frequency is constant, so they operate at 9 gigahertz frequency, and for that they need a magnet 0.33 Tesla. This kind of magnet we actually require for this frequency to operate. And similarly, sometimes some instruments use higher frequency. Some instruments use higher frequency. They use 35 gigahertz. Some instruments they use 35 gigahertz frequency. For that they need the magnet of strength 1.4 Tesla. But it is actually a bit difficult to operate the instrument at higher frequency or at higher magnetic field. So it is better to operate such instruments at this frequency, 9 gigahertz frequency, which actually needs a lower magnet also. As we have read that in NMR spectroscopy we use some reference, like in NMR we use TMS, tetramethyl silane, as reference. Similarly, in EPR we use some references of known G value. Here also we use some references where the G value is known. G value is the spectroscopic constant, or we can say Landy splitting factor. This we will study in subsequent lectures. So in EPR spectroscopy, we also use some references. What the most common reference is DPPH. DPPH is diphenyl picaryl hydrazine cation, and sometimes we use pitch also. Pitch is actually charcoal plus KCl, and DPPH has G equal to 2.0036, and this pitch has G is equal to 2.0028. So they are of known G value. This type of references we can use during taking the EPR spectrum. Now we will move to the structure of this DPPH. Diphenyl picaryl hydrazine cation. Its structure is like this. So this is the structure of DPPH. So here you can see diphenyl, one phenyl and another phenyl, and there is a picaryl group also. It is a derivative of picric acid, trinitrobenzene, and then we have a hydrazine derivative, here hydrazine cation. So why this has been used? Because the lone pair on this nitrogen that will actually be involved in the resonance with these two phenyl rings, so they will be more of concentrated towards these rings, so there will be less effect of these electrons on this nitrogen. Similarly, there are 3 electron withdrawing groups on this benzene ring. They will also actually lessen the electron density close to this N positive. They will take away the electron density from this cationic nitrogen. So the electron, unpaired electron here, that will not feel much influence from the neighboring electrons. That is why it is G value is equal to 2.0036 is almost equal to that of the free electron, that is equal to 2.0032. So they are almost equivalent. That is why it is being taken as a reference during this type of spectroscopy. Thank you very much. This is all for today.